Welcome, Adrian.
Thank you very much, James. Hello, everyone, and thank you for coming to my talk. Today I will be talking about Vesta Control Panel Admin Takeover issue that I discovered and exploited. And in particular, I'll be talking about exploiting reduced seed entropy in bash random. Now, if this doesn't make much sense, that's because I had a lot of palinka last night. But I will do my best to try to explain it, and you can also feel free to ask me questions at the end. So, as I said, I'm Adrian Tiron. I'm a founder and principal consultant at Forbridge. I got a couple of certifications in offensive security, the classical OSCP, certified red team operator and red team lead, a couple of cloud security certifications, and a few more certifications from offensive security like OSEP, and now working on OSW, WE, which is about exploiting web applications, as I'll be talking today. And I've been speaking at a couple of conferences lately, like Blue Hat, besides Dresden, besides Kent, and today at besides Budapest, so thank you very much for having me here today. What is this talk about? Well, it's about application security, which is one of the core things that we do at Forbridge. Basically, it will be a mixture of web application exploitation and also binary exploitation, as you'll see. We'll be starting with reviewing some PHP code, and then we will dig deeper into a bit of C code. We will dig a bit into PHP internals and bash internals, and we will come up with a very interesting exploit, I would say. Also, it is about exploiting the password reset tokens, which is one of my favorite things to investigate when looking at a web application. And as you can imagine, that is because it's unauthenticated attack surface, and this is one of the coolest things that you can look at as a hacker, right? Because it's unauthenticated, you don't need credentials, and it's also a very small attack surface in general. So if you find a critical vulnerability in the unauthenticated attack surface, that is a big win for us as hackers. This also is classified as a cryptographic failure, right? Because the password reset token should be cryptographically secure. So OWASP Top 10 in the latest update in 2021, it is second place, as you can see there, under cryptographic failures. So first things first, a few words about Vesta Control Panel. It is a web-based control panel. It is used for managing Linux servers. It's similar to cPanel, VHM, Plesk, and as a side note, we did research into all these control panels previously, and we found some very interesting vulnerabilities. In case you're interested, you can find more write-ups on our blog. It's used to manage domains, databases, websites, cron, backups, pretty much everything you would expect from managing a Linux server from a web interface. It's pretty lightweight. From an architecture point of view, it's written in PHP, and PHP calls into some bash script, and these bash scripts do all the heavy lifting. And as another side note, they seem to have been acquired last year by a company called Outroll, which is around the time we reported this critical issue to them. This is how the dashboard looks like. Pretty straightforward stuff. Very intuitive and very easy to use. You can manage, like I said, web, DNS, mail servers, databases, etc. Pretty standard stuff so far, right? So, we have access to the source code, which we found on GitHub. Therefore, it makes sense to do a white box pen test. Most of the projects that we do, I would say, are black box. But if you actually want to find some very interesting, very cool vulnerabilities, I always recommend to review the source code if you have access to it. So, as I said, the code is PHP. There was no obfuscation. If you ever looked at commercial PHP applications, sometimes they're obfuscated with IonCube or whatever encoder, so you need to find a way to deobfuscate it, etc. In this case, this wasn't necessary. Also, the code is pretty simple, I would say. I mean, there's no frameworks, there's no object-oriented code, there's not, abstraction layer over abstraction layers that make things hard to review. And we also looked what vulnerabilities have been reported previously, and there were a few of them that got patched. Previously, there were things like argument injection, command injection. So obviously, the low-hanging fruits have been fixed already. So I was wondering, can we find one more critical? Because, as hackers say, there's always one more. First, however, before digging into the core issue that we found, let's review some dodgy code patterns, because we had to go down the rabbit hole until we found the issue that we exploited. So let's see some interesting things first. The first dodgy code pattern, it was when managing cron scripts. So, first thing at the top here, if you look, there's no explicit authentication check. And here at the end, at the bottom of the page here, it calls an exec function, which calls the add cron job script, and there's a couple of parameters. Now, most of these parameters are passed through escape shell arg, which is fine, because that is the way they should do it. They're sanitizing all the parameters before passing them to the exec function. So, what does it check at the top? It checks if the request received is a post, so that's a very simple check and very easy to bypass. It also checks for CSRF issues. If you see here, it checks if there is a token as a post parameter and if this token is different to what is in the session. So that's a basic CSRF check. No issue here to bypass. So far, so good from an attacker's point of view. And here at the bottom, when it calls the add cron job, it passes the user variable. But this user variable does not go through escape shell arg, so there's no sanitization here. So I was wondering, is it possible to inject in this user variable and achieve some command injection? That was my first thought. So the question was, where is the user variable coming from? It comes from the session variable. And basically, like I said, there's no explicit authentication check. It's just an implicit authentication check. So they rely on the fact that this variable session user will always be set. So I thought maybe I can find some session pollution vulnerability. Like maybe I can find some script which writes into this session variable something that I can control, and maybe I can go back and to inject into that exec function. Fortunately for them and unfortunately for me, I couldn't bypass this. So it was a dead end. But I thought it would be like an interesting avenue of exploitation. Let's move to the second dodgy code pattern that I noticed, which was in the Gen SSL certificate. Again, at the top of the script, there's no explicit authentication check. So what this means is basically that I was able to generate TLS certificates as well. I was just triggering the script with whatever parameters I wanted, and I was able to generate a TLS certificate on the file system. Again, at the bottom, before calling the bash script, all the parameters are passed through escape shell arg, which is okay from their point of view. So here I thought, okay, I saw escape shell arg here, I've seen it being used previously, so I thought, okay, maybe I can find some 0-day in PHP. So I wrote a fuzzer with libfuzzer, and I tried to exploit escape shell arg, but I couldn't find any 0-day or any bypass. I also tried to fuzz escape shell arg function with some very basic PHP script, and I throw at it some weird characters with weird encodings. I thought maybe I can terminate a bash PHP string, like enclose the single quotes and then add the command or whatever. That didn't work either. So now let's look at the main issue that we discovered, which is in the password reset process. As you can imagine, when you trigger the password reset process, you'll receive a very standard email which contains the username that you try to reset the password for. In my case, admin, because I'm trying to take over the admin account, right, which manages the full server. And you receive this code, this random code. So the obvious question is, how is this code generated? Can I predict it? Can I brute force it? Can I attack it somehow so that I can reset the password of the admin account and take over the server? So I started reviewing the code. This is the PHP code which initiates the password reset process. So basically, what it does, as I said, it receives the user, which again goes to escape shell arg, which is fine from a security point of view, and then it calls the bash script list user. So this list user script will read information from a file about our admin user. And in this file, there is various things stored about our user. And one of these, it's in JSON format, because you see here it calls JSON decode to parse this file. And it reads the R key field from this file. And then it uses the hash equal function to check if the R key variable, which is read from the file, is equal to the post code variable, which is the code parameter from the URL that we just clicked, right? And this, if this is equal, it means, okay, I have the right token, and then I can call this change user password, and it allows me to change the password of the admin user. And it calls the exec function again to reset the password. So, obviously, what is really important here is the R key variable. R key variable, you can see here, is stored in the user conf, because every user in Vesta has this file associated with it. And it contains a couple of things, basic settings that are configured. It contains the password, which is stored in MD5 format. Obviously, this is an issue, but this is not the main thing that we're interested in right now. And at the bottom, it contains this R key. And this R key is necessary. You need to have this right R key variable in order to be able to reset the administrator's password. And one very important thing that I need to mention here. In order to reset the admin password, you have this R key. And once you reset the password, this R key will be regenerated. So bottom line is that you can't just go to the password reset functionality, click on password reset for the admin user, and receive a new R key every time. No, you'll always receive the same R key. Doesn't matter how many times you click on it, how many times you try to reset the password. You'll always receive an email with the same R key. And once you reset the password successfully, then you will achieve two things. You will change your password, and you will also generate a new R key. So this is an important thing to understand here. Let's look now at the bash script that actually changes the user password. So the PHP API, as I mentioned, calls this bash script. And as I explained previously, when doing a successful password reset, you are achieving two things, which are highlighted here. The first thing is that you generate a new R key, and then the next thing is that you update the user password, which is, as you see here, the second line. It calls the update user value, and it stores the new password in MD5 format. And if you also look here in this script, a new R key is generated, and this new R key is generated with the bash function called generate password. So I can tell you, because I looked at all the code, this generate password is used often in Vesta, and it's used to generate new reset tokens or new passwords, or every time they need a new, let's say, secure string. We'll see what this secure string is actually, how does it actually look like and how it's generated. So we need to review the generate password function now. If you look at this generate password, basically here it generates a string with a length of 10 characters, and these 10 characters are chosen from this matrix string, which basically contains all the alphanumeric characters. So from 0 to 9, all lowercase characters and all uppercase characters. And basically it does a basic while here until it generates a string with a length of 10 characters. And what it does is it uses the bash random variable to generate a random number, and then it uses the modulo operator to basically generate an index within the length of the matrix string. So it chooses every time for 10 iterations, it chooses an index, a random index within the matrix string, and that is your new password reset token. Now, obviously, I did a bit of Googling, and the first thing that popped up was that the random variable is not crypto secure, and it's a pretty small number between 0 and 32,767 or something like that. So I thought, okay, it's not crypto secure, this looks interesting and potentially exploitable. So I did a bit more Googling, and I found out this project on GitHub, which is called Bash Random Cracker, which was created by a gentleman called Horian Holter. I'm not exactly sure how you pronounce it, but credits to him for building this project. And basically, you can use this project to guess the seed and predict random numbers. So you can see here, I'm calling bash rand with the crack argument, and then I feed it 3 random variables. And what it does is, first thing, it guessed the seed, which is 2 billion something, and then it is able to predict the next 3 random numbers. And I verified this by echoing the next 3 random numbers that are generated in bash, right? And you can see that these numbers here are a perfect match with what bash random cracker predicted. So it works very well. And the other interesting thing is that you can also seed the random variable, and it will always generate the next random numbers because it's very deterministic. So I'm seeding it here with lit or 1337. I'm echoing 3 random numbers, and it gives me some random numbers. And I do this same thing again, and again I'm getting the same random number. So giving it the same seed, it will always generate the same random numbers, which is very good for us because it means it's a sure thing that we will be able to exploit this if we get the seed right. So the next thing I did was I started investigating this GitHub project. I reviewed the source code because I wanted to understand a bit better how does this actually work in practice, what's happening behind the scene. And I looked at the function which calculates the seed, which you can see here on the right side. So basically it's very simple stuff. If the seed is 0, mainly it means if you haven't seeded explicitly, it will use a default seed, which is 1, 2, 3, 4, 5, 9, 8, 7, 6. And then it does some basic arithmetic operations on it, some division, some multiplications, etc., which is very deterministic. And basically, at the end, it will return the new seed. And here on the left side is the actual algorithm. I'm not sure if it's very clear, but I will try to explain what it does. So basically, there are two versions of the algorithm. One is in Bash version 4, and then there's also a newer version called in Bash version 5. So essentially, every time you're asking for a new random number, it generates a new seed using the function on the right-hand side, and then basically it does again some very basic arithmetic operations in order to calculate a new random number. And it does a very basic check at the end. Basically, it verifies here at the bottom if the new random number is equal to the previous random number. So if they're equal, the function will call itself one more time to generate a new random number. So this is just a basic check to make sure that it will always provide a new random number different to the previous one. That's it. So the next thing that I was curious about, okay, how is the seeding actually done in Bash? So I had to dig into the Bash internals right now, which is pretty basic C code. It sounds complicated, but believe me, it's not that complicated. So I found the function seedrand, which does the seeding of the random generator in Bash. So what this function does is it calls getTimeOfDay API in C, right? And it reads the current timestamp and the current microsecond into the TV variable. And then it calls the sbrun function, and as a parameter, it passes the seconds, the microseconds, and the PID of the current process. And it simply XORs these three values. So it just does an XOR between the current second, current microsecond, and the current process ID. Now, please pay attention to this highlighted area when it calls sbrun with these three values, because this is very important, and this is where the key vulnerability is. But to be honest, I didn't notice it in the beginning. Like, it took me a while, maybe a couple of days or something, I know, until I actually realized what the issue is. So, until I realized what the issue is, I had to go through a couple of steps, and I was brainstorming for some ideas of what could I do to exploit this. And the first idea was to brute force all values, 4.3 billions. Why 4.3 billions? Is because if we go back, this sbrun function, the parameter of the function, it's an unsigned long variable. So unsigned long variables are stored on 4 bytes, which means 4.3 billion values roughly. So my first idea was obviously brute force this. This is a terrible, terrible idea, very bad idea. I realized quickly that it's going to take weeks, it's noisy, and it's just not doable, and it's not practical, and it's not sexy, basically. So then I looked at a couple of other things. As I mentioned, one of the values that is passed is the get PID, which is the process ID. In general, this is stored on 2 bytes, and it's pretty well known in the industry that it's brute forceable, because it's a small value. On 2 bytes is brute forceable. The next thing, as I discussed, microseconds are used. Microseconds basically means that it is a number between 0 and 1 million, and you only need 20 bits to represent 1 million. So 20 bits, again, it's a pretty small number. This is also brute forceable. So the most important thing, if we go back again, the only remaining thing is the timestamp, the current timestamp. I realized, so I thought maybe I can find some sort of information leak to leak that timestamp. So I did, let's say now I did like a black box text. I looked at the endpoints and I was thinking, okay, is there any endpoint that leaks that timestamp at the moment of the password reset, because that was the timestamp that I wanted. So I did find a couple of endpoints. However, the problem with these endpoints was that they were all authenticated. So it was not very useful. It was a bit of a chicken and egg problem, if you will. Because I'm like, well, I need to be authenticated to get that timestamp, but if I'm authenticated, I don't need it anymore. I need some sort of authentication bypass. I need an unauthenticated endpoint to give me that timestamp. So this wasn't useful for me. It was a chicken and egg problem. It didn't solve anything. And again, just to be clear, the timestamp that I want is the timestamp at the moment of the password reset. That's it. That's the only timestamp that I'm interested in. Because if I get that, I figured it out that I could brute force the PID, I could brute force the microseconds. That would be doable. And again, if you have any other ideas or any other tricks, feel free to share it. I'd love to hear them. So, at this moment, I was really out of ideas. And one of the things that I do when I'm out of ideas, and one of the things that I actually like to do, is to review some PHP source code, which is written in C. And one of the reasons why that is probably because I'm an ex-PHP developer, and I understand a bit of basic C code as well. So I was like, let me look how PHP does certain things. And in PHP, there is a function, if you're familiar, called LCG value, which generates pseudo-random numbers. Okay, and this LCG value function uses the LCG seed function to seed its number generation process. So I was like, let me have a look. Let's see how seeding is done here. Like, we've seen how seeding is done in Bash. I'm like, let's have a look now. Let's see how the PHP guys are doing it. So, in this LCG function, there are two variables that are used, S1 and S2. Okay, here you can see the S1, and here at the bottom you can see the S2 variable. And in a very similar manner, this LCG seed function also calls get time of day. So this function also needs to read the timestamp and the microsecond. And then, again in a similar manner, this function does an XOR here between the second and the microsecond, only it does a left bit shift by 11 positions here, and then lower, when it sets the S2 variable, again it does an XOR, and it does a left bit shift by 11 position. So I looked at this, and this got me thinking, like, why does it do a left bit shift? Certainly, as a developer, you can remove that left bit shift, and it will still work. So this got me thinking, and I thought about it for a couple of days. And I was like, there has to be a reason for this. Like, there has to be some sort of security implication or something. And yeah, I had to start thinking about this. Let's have another look again, how the Bash guys were doing the seed generation. You can see here that they're simply XORing the three values, the seconds, the microseconds, and the bit, right? We're simply XORing three values. There's no left bit shifting. There's no sorts of bit shifts, nothing. So I was wondering, could this be a problem? Because, you know, as a developer, as an ex-developer, I was thinking, this would work even without the left bit shift, but there has to be a specific reason why that left bit shift is there. And then I had an aha moment, or an Eureka moment, when I figured it out. So the issues with the seeding in Bash are the following. If we look, let's start looking at all the variables one by one to see how this issue compound basically and lead to a practical exploit. The problem with the tvsec, which represents the current timestamp, in memory, it allocates, there are 8 bytes allocated for this variable, but in practice, only 4 bytes are enough, and you can store timestamps from 1970 to about 2038 as a year. As I mentioned again, regarding the microseconds, they also occupy 8 bytes in memory, but in practice, it only uses 20 bits. because there's only 1 million microseconds, and 20 bits are enough to store this value. Now the get bit variable. It occupies 4 bytes in memory, but in practice, these values are very, very small. So I did some testing, I created some fork bombs, and the maximum bit that I achieved was around 660,000, which again needs 20 bits. So any value up to 1 million, you can safely represent it on 20 bits. But again, the bit value is the smallest value out of all these 3 values by far. So usually you need a lot less than 20 bits, like maybe 10, 15 bits, something like that. So then I realized, when you XOR these 3 values, what's going to happen is you're going to have the timestamp, and because microseconds and get bit are represented, let's say both of them on 20 bits, you will only be changing the lowest 20 bits of the timestamp. The upper 12 bits will always remain static. And this is what I mean by reduced seed entropy. Because they don't do any left bit shift, the upper bits of the timestamp will always remain static, and this is what will create a condition for us that will allow us to exploit this vulnerability. Now, to make a note here, get bit could be the only deal breaker for an attacker here, but as I mentioned, this would have to be like a very, very high number in the billions, so that when you do that XOR, it changes some of the upper bits of the timestamp. But I ran this exploit a couple of times, and this was never an issue. So, to summarize all the issues, by only changing the lower 20 bits of the current timestamp, we reduced the seed entropy, and what will happen in practice, the seed will fall within an interval of approximately 12 dates around the current timestamp. So, to give you a practical example, let's say I do a password reset right now. Today is the 21st of May, I believe, right? If I had the right, yeah, okay, I didn't have that much polling, I guess. So today is 21st of May. If I do a password reset today, there will be a new timestamp, and it will be, let's say, between 1 week before this date and 1 week after this date, roughly that. So you can brute force this interval. So on the next slide, we'll calculate the minimum and the maximum timestamp. After we do this XOR operation, you'll see that basically we will set all the bits, all the lowest 20 bits to 0 to get the minimum, and then we'll set all the lowest 20 bits to 1 to get the maximum timestamp. So I think it's pretty clear that the timestamp is really the only relevant factor here. The bit of the process and the microseconds are pretty much irrelevant. So some very simple PHP code for visualization. Here at the top, I'm getting the current timestamp. Let's say it's today, 21st of May. And then I create a mask which sets the lowest 20 bits to 0. You can see this here. And then I'm outputting this first timestamp, which is the minimum timestamp. And then I do the opposite thing. Basically, I set all the lowest bits, the lowest 20 bits to 1, and I calculate the maximum, and I display this new timestamp. And here you can see the output. So I did this test at some point last year. It was the original timestamp was the 8th of July, and then the minimum was 29th of June when I set all the lowest 20 bits to 0, right? So it was like 9 days before the original timestamp, and then I calculate the maximum, and the maximum result was 11th of July. So 11th of July was 3 days after the original timestamp. So it started from, in that case, from -9 days to +3 days from the original timestamp. 12 days interval in total. So, first things first, I started creating a local exploit, basically to prove that this theory is actually working. I extended the project from the previous guy, which is called bash random cracker once again. I added a method to brute force all the 4 billion seeds, and this is because I was lazy. Obviously, you can optimize this a bit, which we'll discuss in a moment. But I was lazy, and I did this in Rust. And one thing I noticed is that Rust is extremely fast, so speed was not an issue at all. And basically, I checked if I can generate a password reset token, which is identical to the one stored on the file system in the user conf file. So our suggestion, my suggestion, is that I'm making an assumption here. To be fair, the assumption is that the admin user reset his password in the last 3 years, or that Vesta was installed in the last 3 years, right? So I think 3 years is a reasonable assumption, and what we propose is to go back, let's say, from today, the moment when I'm starting the exploit. I'm starting from the current timestamp, and I'm going back for 3 years, and I brute force all this timestamp. And I think this would give me like a very good probability that I will exploit this. And if I have to, if I really have to, I can go back 1 more year, 2 more years, 3 more years, and it doesn't make a large impact on my probabilities or on the duration of the exploit. But that would be like a really bad scenario. I think 3 years is pretty reasonable. So you can see here the code in Rust where I extended the bash random cracker. Basically, as I mentioned previously, I have brute forced all the timestamps, 4 billion values, simply because I was lazy and I didn't want to apply any optimization. Plus, I was like very new in Rust code, so I got the proof of concept working. It's working, it's fast, it's good enough, like, let's go with it. And of course, I fed the password reset token in user conf file, and in a couple of seconds, really, it already found the password, the seed for the password reset token. So it works very well and very fast. Yeah, you can see here how I called it. This is bash run called. I added the argument password, and as a parameter, I passed the password reset token, which you can see here at the bottom. It was stored in user conf file, and it starts brute forcing, etc. from 1970, and it found the seed that was used to generate this password reset token, which is a timestamp that corresponds to the date 28th of June last year, which is like around the date that you saw me using previously. So I realized, okay, the local proof of concept is working very well. And then the next step was obviously I'm going to port this algorithm to Python, and I'm going to create a plugin for Turbo Intruder. In case you're not familiar, Turbo Intruder is a plugin for Burp Suite, which was created basically to make, as the attacker say, as the developer says, James Kettle, to make the billion request attack feasible. So it is like a custom TCP/IP stack. It optimizes everything so that it can go very fast and be able to send a billion requests in reasonable time. And I created my custom script, which is called Vesta POC. You can find it here in our GitHub repository. And as I said, we propose to brute force all timestamp in reverse chronological order. So if we start today, we would start from 2025, 21st of May, and we would go back for 3 years. So in practice, this would mean that we would have to brute force 31.5 million attempts per year, right? I calculated here. And if we go back and brute force this for 3 years, it means 95 million requests, which is like 98% optimization, right? And if you want to see more Turbo Intruder optimization tips, you can see this blog here where we exploited some vulnerabilities in concrete CMS. So yeah, in the end, we managed to cut it down from 4.3 billion to 100 million requests, which is, again, 90% reduction. And here you can see the glorious win. I used it in Turbo Intruder. I was able to brute force the password reset token, and I was able to set the admin password. And here you can see I'm already logged in once I was able to achieve this. And I'm getting all this information about the admin account. I think, okay. If you'd like to see more of our leading research, you can see our research on concrete CMS, which again, we exploit the double race condition to achieve remote code execution. We also had the field dating application last year. You will see a talk about this today. And we also extended the Evil Jinx toolkit, which is used for phishing. Basically, we realized it was missing a lot of DNS records, so we added this capability for it in order to increase our phishing chances, in order to increase the probability that the email will land in the victim's inbox. Yes, Q&A?
Adrian, I think if you have any questions, there's the Discord channel on the B-Sides website. Adrian, you're going to be around?
Yep.
So obviously you can speak to Adrian in the common areas between the presentations. So thanks very much for all your energy and making it through that.
Thank you very much.
Having sampled the local delights of Budapest.
I will.
Yeah, and safe journeys back to London, I believe.
Yes, thank you very much, James.
Please show your appreciation for Adrian.